Hello, I'm Seema and welcome to part 8 of the chapter Hydrocarbons. We were doing the methods of preparation of alkanes and I told you that there are three methods, three sources from which we can prepare alkanes. The first is from unsaturated hydrocarbons, the second was from alkyl halides, and the third method is the third source is that we can prepare alkanes from carboxylic acids. In this video, we are going to discuss the third method, that is, how do we prepare alkanes from carboxylic acids. When you prepare alkanes from carboxylic acids, there are further two ways how you can do it. So the first way is by the decarboxylation of the sodium salt of the carboxylic acid. So let us see what happens here. You take the sodium salt of carboxylic acid, and the sodium salts of carboxylic acids are heated with soda lime. What is soda lime? Soda lime is a mixture of sodium hydroxide and calcium oxide. So you heat it up with a mixture of soda lime, that is sodium hydroxide and calcium oxide. Out of these, the calcium oxide does not participate in the reaction. So you could say if you're adding soda lime, the lime part acts as a catalyst and it's the soda part, that is the sodium hydroxide, which reacts. So you heat it with soda lime and it gives alkanes, and the alkanes that they give, the point that you have to remember is the alkane that is produced has one carbon less than the carboxylic acid or the sodium salt of the carboxylic acid that you started with. So since we are preparing it from carboxylic acids, you'll first turn the carboxylic acid into its sodium salt. Then you will use the sodium salt of that carboxylic acid. You'll make it react with soda lime. When it reacts with soda lime, it will give you an alkane which has one carbon less than the original carboxylic acid. We call this decarboxylation. And the reason we call it carb means carbon, ox means oxygen, and D means removal. Since it is removing carbon and oxygen, it's basically removing carbon dioxide. And that additional, since you started with carboxylic acid, the first thing that you did was you turned it into its salt, that is the sodium salt. So it removes that salt also that you had originally added. So the reaction is that you start with the sodium salt of the acid. For example, here we start with sodium. The sodium salt of the acid. Which acid is it here? CH3COOH. It is acetic acid. So this is sodium acetate. Sodium acetate reacts with soda lime. Soda lime, the lime is put here as the catalyst, and sodium hydroxide. So what happens? The carbon dioxide here, this carbon, the two oxygens and the sodium here. These two, Na2, and two oxygens here and one carbon, CO, and 3. The third oxygen is here. So the hydrogen that is left here, this hydrogen goes and combines with the carbon here. You see the bond between carbon and carbon is broken. The CO2Na joins the NaO to result in the formation of Na2CO3. And the hydrogen that is left goes and joins the carbon, the carbon before the one which had the carboxylic acid functional group on it. So, and it results in the formation of the alkane, that is in this case it is methane. Since the carboxylic acid was ethanoic acid or sodium ethanoate, therefore the alkane that you got had one carbon less, therefore it was methane, right? And sodium carbonate is formed. So there's a question, a solved example in your textbook, question 13.6. which says that sodium salt of which acid will be needed for the preparation of propane. If you wanted to prepare propane here, which sodium salt of which acid would you use? Since propane should be formed after the loss of one carbon atom, therefore the acid should be which sodium? It should be sodium butanoate, because you want propane. So it should be sodium butanoate. So you will, and sodium butanoate is obtained from which acid? It is obtained from butanoic acid. So we'll say sodium salt of which acid will be needed for the preparation of propane? Butanoic acid will be, the sodium salt of butanoic acid will be needed, and you have to write the equation. The equation is the same. You have to write butanoic, the sodium salt of sodium butanoate will be written here. CH3, CH2, CH2, COO negative, Na positive. The COO negative, Na positive will be removed. NaO will be used to form Na2CO3. This hydrogen will come and join this carbon. So you'll get CH3, CH2, CH3. That is propane. And you get sodium carbonate. So this was preparation of alkanes by the decarboxylation of the sodium salt of carboxylic acids. That was the first method. The second method is known as the Cobb's electrolytic method. As the name suggests, we carry out this reaction with the help of electrolysis or by passing electric current. And since we are doing it under, what is it? It is a method of preparation of alkane from carboxylic acids. So we'll again be starting with carboxylic acids. Carboxylic acids are not very highly ionic. Their ionic nature is not too much. So we try to convert them into the sodium salts to make them more reactive or more ionic in nature to enhance the speed of the reaction. And in this case, of course, the sodium was needed to form the sodium salt, that is sodium carbonate. So here also we start with the aqueous solution of the sodium or the potassium salt of the carboxylic acid. Why? So that the carboxylic acid becomes more ionic in nature, and as soon as it goes into the water, it dissociates into its ions. So an aqueous solution of sodium or potassium salt of carboxylic acid, if we had used simply the carboxylic acid, even that would have ionized, but the degree of ionization would be very less. So you would not get enough product. You want that carboxylic acid really to break down completely. So to do that, you will make a salt with a strong metal like sodium or potassium. Now it is so ionic that as soon as it goes into water, it almost dissociates completely. And therefore your yield will be greater. That's the reason why we use the sodium or the potassium salt. So an aqueous solution of sodium or potassium salt of carboxylic acid on electrolysis will give alkane. And this alkane will always contain an even number of carbon atoms. It has an even number of carbon atoms. In the previous video also we had a reaction in which we had the Wurtz reaction. In Wurtz reaction we said you get an alkane with even number of carbon atoms. But in that case you could have chosen your reactants, two reactants, in a way that one was even and the other was odd. Then you would have got a product with odd number of carbon atoms also. There was a possibility of an odd number of carbon atoms, a product here with odd number of carbon atoms. But here it is exclusively, you will always get the hydrocarbon with even number of carbon atoms. So what happens, as the name suggests, that it is electrolytic and you're using a salt solution, that is, and what is the salt? It is the sodium salt of the carboxylic acid. You dissolve it in water, it ionizes. Now you pass electric current through it. When you pass electric current through it, how will you pass electric current through a solution? By dipping two electrodes in it. The positive electrode is the anode and the negative electrode is the cathode in electrolysis. If you remember, when you make cells, it is the opposite. But in electrolysis, the positive electrode is the anode and the negative electrode is the cathode. So the negative ions will be attracted to the anode and the positive ions will be attracted to the cathode, which is negatively charged. We know this. So what is the reaction that takes place? Let me just read this out now. An aqueous solution of sodium or potassium salt of a carboxylic acid on electrolysis gives alkane containing even number of carbon atoms at the anode. Why? This is the sodium salt of an acid. We took the same acid, sodium acetate. As soon as you put it in water, it is going to ionize. The acid is going to ionize into what? It is going to ionize into CH3COO negative and Na positive. But when you carry out the electrolysis, the water of the solution also reacts with it. And this is the overall reaction here. So the water also reacts with it, and what happens? You get CH3, that is these two, you have two molecules of sodium acetate. So these two CH3 will join together and give you ethane. And the acetate, that is this carbon, COONA positive, and the water, they will all react and result in the formation of the other products, that is carbon dioxide, hydrogen, and sodium hydroxide would be produced. Sodium, water, you know, water also ionizes into H positive and OH negative. So the water, when it ionizes into H positive and OH negative, the sodium and OH negative will join together to form sodium hydroxide, which is a strong base. And you will get carbon dioxide straight from here, CO2 is released, and the excess, the hydrogen that is left then, that out of H positives, 2 H positives will be formed and OH negative. So the 2 hydrogens that will be there, they will result in the formation of hydrogen gas. Now, how does this reaction take place? How do we get these products, and why do we need electric current to carry out this process? So let us see what is the path that they follow. The path they follow is that the first thing, you put the salt in water. As soon as you put the salt in water, even before you have passed electric current, the salt sodium acetate, 2 moles you start with. You need a minimum of 2 moles. Why? We saw here itself that these 2 methyl groups would be joining together to form the ethane. And that is, from here itself you get your hint. Why will you always get even number of carbon atoms? If I have 1, which is an odd number, 2 ones will join together to give me an alkane with 2 carbon atoms, which is an even number. If I had 3, then 3 plus 3 would give me 6. If I start with an even number, for example, if I had the acid was sodium propanoate, then I would be left with 2 carbons here, but propanoate would be 2 carbons, and this CO2, this will form CO2, this will form sodium hydroxide. So I'll have 2 ethyl radicals which will join together to give me butane. So I will always get a hydrocarbon or an alkane which has even number of carbon atoms. That having said, let us come back to the pathway now. So the first thing that happens when you add the salt to water is it ionizes. It breaks down into the positive ion and the negative ion in water. So the positive ion here is Na positive, which separates out, and CH3COO negative, that separates out. We know oxygen has how many electrons in its outermost shell? It has 6 electrons in its outermost shell. And in order to complete its octet, it needs 2 more electrons. Now it completes its octet by forming a covalent bond with this carbon atom, and therefore there is a bond pair here. So oxygen has 2 electrons here, but the negative charge is giving it that 1 electron which was required. It needed 2 electrons. It gets 1 from carbon by the covalent bond, and the other electron is obtained from sodium in the form of the negatively charged electron, which totally belongs to the oxygen now. So oxygen here has this 1 electron which is giving it the negative charge. Since it is negatively charged, this ion is negatively charged, it will be attracted by the positive electrode. So at anode what happens? The negatively charged CH3COO negative ion is attracted towards the anode. The anode now, it removes 2 electrons from it. It is the positive electrode, that is anode. The negatively charged ions move towards the positive electrode anode, and they lose 2 electrons. Why do they lose 2 electrons? One ion loses only 1 electron. This negative charge, the negative charge will be lost. So when the oxygen loses that negatively charged electron, we have 2 of these ions, therefore we say 2 electrons. Actually, one ion loses that 1 electron which it had got from sodium. After it loses that 1 electron, how many electrons did this oxygen have initially in this structure? It had 8 electrons. 6 electrons of its own, 1 electron from carbon, and 1 electron which was giving it the negative charge. So it loses that negative charge, but now it has a pair, 1 pair of electrons here, 1 pair of electrons here, 1 pair of electrons, and 1 electron less than the octet. So in this structure you can see this. that you get CH3CO, and this oxygen now has it had 6 electrons of its own. It has 1 electron from carbon, but that 1 electron it had from sodium, it has lost that. So this electron becomes the unpaired one. This electron is unpaired, and any species which has an atom in which there is an unpaired electron, it is not charged, it is neither positively charged nor negatively charged, but it is lacking in 1 electron, is known as a free radical. Right? And it's another reactive, a very reactive intermediate, you can say. Free radicals do not exist in nature just like that. A free radical is a very temporary state. It is immediately going to react and form a molecule. So this results in the formation of this acetate free radical. And since we started with 2, you get 2 free radicals by the loss of 2 electrons, 1 electron from each of the ions. After you get this, what happens? This free radicals as it is are very unstable. And this free radical is not only unstable due to its being a free radical, it is a bulky one, it's a huge molecule. So the carbon dioxide says, I don't really need this nonsense to be so bulky. So why don't I just move out of the molecule? The carbon dioxide easily moves out of the molecule, taking with it this electron. This oxygen has 1 electron less, but this carbon, what it does, it takes the electron of this carbon and it moves away and forms carbon dioxide neutral. But now this carbon and this carbon had its electron, which it was completing its octet by making 4 bonds, 3 with hydrogens and 1 with carbon. So now when this carbon takes away its electron, this carbon becomes electron deficient. It has 1 electron less than the octet. Therefore, this carbon now becomes the free radical, right? The free radical now is the methyl free radical. And carbon dioxide becomes a neutral molecule, it's a gas, it bubbles out and it goes away. It says, I have nothing to do with this molecule. There's too much instability here. I'd rather be a gas, I'd rather be free. So carbon dioxide escapes and leaves, and now as this happened, do you notice this carbon is lost? Which started when we started with the carboxylic acid, that carbon is lost just as the carbon was lost in this case also. But in this example or in this method, what happens? The 2 free radicals that are formed, they are both free radicals. Both of them are deficient in 1 electron. Both of them are looking for something to complete their octet. What could be easier than combining with each other? One carbon says, I have 1 electron less. The other methyl group, methyl free radical, also has a carbon who says, I have 1 electron less. So why don't we just join? Let us just form a bond. So the 2 methyl free radicals, they simply form a bond with each other, resulting in the formation of an alkane. And the alkane is ethane. Ethane is also a gas, we know that. Now, the ethane that is formed, it has even number of carbon atoms. Of course, it has even number of carbon atoms. And that is why we said that it results in the formation of the hydrocarbon or alkane, which has even number of carbon atoms. Now this was the reaction that takes place at the anode, and you have actually obtained the alkane that you were trying to prepare. But since it is electrolysis, what is happening at the other electrode? At the other electrode, you would expect sodium ions that were formed here to quickly, if this ion was running towards the anode, you would expect the sodium to jump towards the cathode. After all, that was positively charged. But sodium is so highly ionic and it would rather stay in the solution. Its dielectric constant is pretty high. So what happens? It would rather stay in the solution. And on the other hand, at the cathode, instead of sodium ions going and gaining the electrons, the water molecule which is present as the solvent, that breaks down. And at cathode, what happens? The water molecule instead gains the electron. And when water molecule gains the electron, it results in the formation of OH negative and hydrogen free radical. Again, the same situation is created. Just as you had the methyl free radical, the hydrogen free radical is formed. And at that site itself, when the hydrogen free radical, not one will be formed. There are so many millions of molecules. So you have millions of hydrogen free radicals which are still being formed near the cathode. And as soon as they are formed, they don't take long to go into the solution and try to go towards the anode and then choose this free radical. No, they immediately combine with each other and result two hydrogen free radicals will combine together to form hydrogen gas, which will also evolve. And our idea was to get ethane, which we got. Now the last point here says that methane cannot be prepared by this method. Guess why? Very easy. You need even number of carbon atoms, and methane has only one carbon atom. So even if I started this is where we started with the methyl free radical. So methyl free, there can be nothing smaller than a methyl free radical. So even if you had methyl free radical, the first product that you will get will be ethane, which will at least have two carbon atoms. So you can never have the gas or the alkane methane prepared by electrolytic method. So these were the methods of preparation of alkanes. And with this, I'll wind up today's video. If you found it helpful, give it a thumbs up, subscribe to my channel, recommend it to your friends, and please keep returning for more videos in chemistry. Thank you for watching, and bye-bye for now.